Okay, homework 3, same section, same pages, right? It's just the stuff that we didn't talk about yet that we're going to talk about today. You'll see right here, so I'm going to say all of these so that, like, this is, I could say in court, no, I did tell them, Your Honor. Even though, yes, it may have been written funny on the board, no, I told them that it was numbers 3, 9, 11, 25, 27, 29, 31, 33, 35, star. That means that there's more work for you to do. And 40. And yes, 40 is even. There's no answer for it, but it's really straightforward. In fact, like there's not much to it at all. 35. So pay close attention. 35, when you're going to do it, it's going to say estimate the value of the limit to 5 decimal places. You're going to do that. You could, it says illustrate part A by graphing the function. That's cool too. You could use any method you want to estimate that. Like you could plug in closer and closer values to where the limit's going. That would be a great way of doing it. I want you to do a little bit more with that one. I want you to identify when you see out to 5 decimal places what that number is. You should recognize that number. That number should be very familiar to you. And I want you to go, oh, this is the same thing, but it does not look like the same thing, something you've seen before. So it's something you've seen before. In fact, it's a limit you've seen before, but it looks completely different than the limit that you've seen before. And I want you to explain why that's the case. How could that possibly be the case? And when you see it, it shouldn't, what I'm saying is maybe a little cryptic right now. And you might say, what do you mean by explain how that's the same? If there's any questions on that after you've, like, if you don't know what I mean by explain to me how this happened, email me. But you should understand, you should be able to figure this one out. But just use words. I want to see words on the page. How could this be? What, first off, so you do 35 as it says in the book. Then the next thing I want you to do is identify what this is. Say like, oh, this is the same thing as this. And then explain how that could be the same thing as something else you've seen. Okay, so if there are no questions, we're going to go... Oh, I wanted to have a problem of the day on the board. So this is your problem of the day. And it's this. Here's I'm going to draw a function f of x. This right here is f of x. And I want you to evaluate these limits here. The limit as x goes to 5 from the left of f of x. The limit as x goes to 5 from the right. And the limit as x goes to 5. We could all do this together. What is the limit as x approaches 5 from the left? Oh, I don't know. Okay, what is the limit as x approaches 5 from the left?
Negative 1.
Negative 1, right? Because, again, it does not matter what the value is. Remember, limits, the way that we're defining them in this class, does not matter what the actual value is. What we care about is what is the behavior of this function as we approach. And we can see, yes, it's getting closer and closer to negative 1, so that limit is indeed negative 1. Now, ditto, what is it as it approaches from the right? 1. Right, because as we go approaching 5, it gets closer and closer to 1. Doesn't matter that the function actually happens to equal 1 there, because we basically, whenever we're talking about a limit, we could pretend that that number doesn't exist, that we just popped it out of the function. It's one way of thinking about it. Okay, now, what about this?
It doesn't exist.
Doesn't exist. And so if I gave you this, you would write D and E. Does not exist. Why doesn't it exist?
Because both sides agree.
Both, right. Both the limit from the right and the left have to be the same. You have to be going to the same place for this to exist. Otherwise we say it doesn't exist. right? There is no limit from both sides here, right? Okay. Okay, that's cool. But now, let's do this a little bit differently. Let's say that instead, let's let f of x be something similar. Let's say, we got that. And let's say we wanted to answer these same questions right here. And in fact, I'm going to be really explicit here. And I'm going to go ahead and say, okay, 1 over x minus 5, 1 over x minus 5, 1 over x minus 5. So there's your f of x. Now, one thing that you're probably always going to do whenever you have something like this, like here's you're given a function or whatever, maybe this is just the only problem right here. I always default to, can I graph this function? Because that's usually going to make your life much easier if you can.
We can, I think.
We can. And like what I'm thinking of is there's a function I know very well how to graph that's almost the same thing. It just doesn't have that bit right there. You know, so like for instance, if g of x is just 1 over x, I'd think, oh yeah, I know what that looks like. And so this is just that function, but it's been, what's happened to it?
Shifted to the right.
Shifted to the right. By how many units?
5.
5. And so you'll see, very similar to something that I had up here earlier. Right? We just take this picture, we've shifted it over to the right, so it must do something like this, and it must do something like that right there. Okay. Now, another thing, like also, if you know, like you have some kind of, this is a rational function, right? There's a polynomial on top. Yes, 1 is a polynomial. There's a polynomial on the bottom. One of the easiest ways of graphing something is to say, well, where does this thing blow up, right? Where is the denominator equal to 0? Obviously, it's 5. So if you're like just doing this, and you know, okay, it's going to be like this thing. Where is it? Oh, is that a shift right or left? I usually always just at the, like, if I do the shift first, like you guys were saying, it's shifted to the right. I always check myself after drawing this by going, is that what we expect? If I plug in a 5? Yeah, okay, so I shifted it the correct direction. If it were this, if it were 1 over x plus 5, and I happened to get it wrong, I happen to say, oh, that's a shift to the right by 5 units, and so it's this, and so I do the same thing. Then I ask myself, wait, if I plug in a 5, oh, wait, whoa, no, if I plug in a 5, nothing blows up. I must have shifted the wrong way, blah, 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 blah. I've said something like this almost every time I've drawn one of these guys. So, beating dead horses is what I do best. So, now here's the thing. Think about the definition of a limit. And forget about these right now. We're only going to think about this guy right here, this first one. Does that limit exist?
Yeah. The approach. Wait. No, infinity.
It would
Negative
go
infinity.
right. Okay, so as we approach from the left, we could see what happens here. Right.
Oh.
So remember that in our definition of a limit, I want to read it exactly so that I don't mess this up. The definition I put up on the board yesterday, it said, or the last time, it said, sorry, oh, I had it open to it. We write limit, blah, 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 equals whatever, and say, the limit of f of x as x approaches a equals L if we can make the values of f of x arbitrarily close to L. There is no number you could write here that you could get arbitrarily close to by getting close to 5. We could say that this blows up. Actually, in this case, since we're approaching from the left and it's going right here, we would say it blows down. We actually say that this blows down. Going from the other way, we'd say it blows up. But what we're going to do is we can say that this thing approaches negative infinity. And we will say that it equals negative infinity. That does not mean that the limit exists, okay? There is no limit. Yeah. There is no limit to here, right? Like, if I say, you know, you could give me any negative number, like negative 10 to the 10 to the 10 to the 10. And eventually, this thing will go beyond whatever that limit may have been, right? And so this limit does not exist. I would really want to say that about 20 more times today. This limit does not exist. But we write this to kind of give you more information, right? It's like, yes, but if I just said the limit doesn't exist, it doesn't really tell me much about the function itself. But I could write this, and you have a pretty good idea of what that function's going to look like right there. Okay. Now, what about from the other side? What do you think we do here?
Positive infinity.
Positive infinity. Okay. And yeah, and you could see that just by looking at the function. As it goes this way, it keeps going up, and that's an asymptote right there. We know that. And so we could say the limit equals infinity. We'll say a few things about it. There's a bunch, and you're going to hear me say each one of these, right? So for this one right here, we could say the limit of f, we're pretending that that's an f of x right there. The limit of f as x approaches 5 is infinity. Or we would say as x approaches 5 from the right is infinity. We'd also say f becomes infinite as x approaches 5 from the right. We could say f increases without bound as x approaches 5 from the right. That's something you're going to hear a lot. Increases without bound. And that's the idea. There is no bound. There is no limit to which this thing will ever stop, right? Any questions about that? Does that all make sense? You're going to hear me exchange those things all the time. I'll say the limit is infinite. The limit is infinity. The limit's positive infinity. The limit's negative infinity. This decreases without bound, right? F decreases without bound as x approaches 5 from the left. We could say, in this case, x increases without bound as f of x increases without bound as x approaches 5 from the right. Neither of these limits exist, okay? What about this one? Does not exist. You cannot, yeah, and is that, we don't do that. Like you would think, well, plus or minus that, but no, we don't do that. We just say, this one does not exist, okay? And that's for the same reasons as before. You can't reconcile both of those guys going to infinity, right? Or going to opposite infinities. That's unreconcilable. You can't just write a symbol there, but let's say we did this. What if f of x were this? And so in this case, let's see what happens.
Then you can plug in anything. Right?
Can I?
It'll know.
So let's go back to the beginning. The first thing I'm going to do is figure out what this graph looks like. This is not the right graph here. What this does, what squaring that thing does, is it takes all these negative values and makes them positive.
Yeah.
Right?
And like stretches.
And it stretches, right? If anything's below 1, it stretches it down more. Because like if you have 1/2 and you square it, now you got a quarter, and so it pushes that down. If it's anything bigger than 1, so when it's higher than 1, it'll stretch it up. So yes, there's some stretching going on, but that's basically the idea right there. Okay, so now let's do this. As we approach from the left, the limit is
Infinity.
positive infinity.
Infinity.
Also, again, that has not changed. Okay, and now what can we say about this guy?
Infinity.
Infinity, and that's how we would do it.
You can plug in a 5. No, right?
Okay, what?
Oh wait, no, never mind. Sorry. No, it's because. Never mind.
Right, we're not playing. Right, you see, we're pretending that 5 doesn't exist, and we're just asking. Basically, this right here, without the plus or the minus up here in the superscript, we're just asking, are you going to the same place as you go from here? And yes, we are going to the same place. It happens to be infinite, therefore this limit does not exist. But we could give you some info about it, right? Like we could tell you, in what way does it not exist? Well, it's because it's going to positive infinity. And it's going in both directions, right? It's from both directions, we're going there. That's why we could actually write something for this one. We couldn't do it last time because one was going to positive infinity and one was going to negative infinity, right? Okay, everybody with me on that?
I do have one question on the
Yes.
homework.
Oh, okay.
When we were given like the different criterias and we had to graph what
Yeah.
it looked like, how do you know if the curve's coming from like the top or coming?
That's a good question. So, is there one? Let's do one.
Okay,
So, what was the number?
Oh.
Here. There should be these ones right here.
Yeah.
Okay. Tell me. Actually, you just tell me what all the criteria are, and we'll go through this. Because I wanted to do one of these, but we ran out of time last time. So.
Limit as x approaches 3 from the left. No,
3
from the right.
From the right.
F of x equals 4.
F of x equals 4. Okay.
Limit as x approaches 3 from the left. F of x equals 2.
F of x equals 2. Okay.
Limit as x approaches negative 2. F of x equals 2.
F of x, and now that's not from the right or left, it's just that?
Yeah.
Okay.
F of 3 equals 3.
And f of 3 equals 3.
And f of negative 2 equals 1.
F of negative 2 equals 1. Okay. Is that everything?
Yes.
We got that copied right? Okay. Cool. Let's talk about this. I did want to do one of these because this could be easy. And so what was your question? Well, let me just talk through it, and if you still have a question, then we'll do that. So, okay. Starting here, I see, okay, so at -2, which I also see there's a limit to -2. Nice, okay, so I'm going to keep those in mind. There's f of 3, and we're also, something happens, and I see we're going to different places as we do that. Okay, so there's two interesting places. One of them is at -2, and one of them is at +3. So I'm going to go ahead and mark these places. Here's -2, and here's +3. So now, let's see what happens. Whether or not these limits do something, I could tell you that when I plug in a -2, I get out a 1. So, we have a filled in circle right here. Here at 1. And regardless of what everything else is doing, I have to have that. That might not agree with the curve. It might actually just be on the curve and there's nothing funny going on. So, okay, cool. The other one is when I plug in a 3, I get out a 3. So it looks something like this. Now, okay, what can we say about the rest of it? Well, this one tells me that as I go to -2, and since there's no plus or minus right there, it must mean from the both sides. Then this function goes to 2. So that must mean that there's a hole here at 2. So maybe the function looks like this, maybe it comes down and comes back up. We don't know that, but what this tells me is that this thing does something like this and something like that. Maybe it comes down, maybe it goes up, I don't know. We're going to need more calculus to figure that out. We're not there yet. So now the only other thing that we know is that in both, oh no, that was from both directions we get a 2, so that makes sense. Does that make sense how I got that so far? Okay. The other thing that happens is as we approach 3 from the left, so as we come this way, this guy also goes to 2. Okay. So it must be, maybe it dips down and comes back up, but as we go to 3, this guy goes to 2, so we have another hole. So maybe he does something like this. Again, no information was given about what happens here. So maybe it came up and came down. Maybe there's an asymptote and they didn't tell me about. I don't know, So it might just be a straight line for all I know. But there's no information on that yet. So this is all I'm going with. I could connect those in any way that I want. Now as I approach 3 from the right, it goes to 4. So I'm going to need a little bit more room here. That was f of 3 equals 3. And we know it goes up to 4. And so it must be as I go to 3 from this way, it's getting closer and closer to 4, but not actually equal to 4. So maybe it does something like that. Or maybe it came up like that. Or maybe it's a sine curve after that, who cares? But the idea is, as long as it does this thing right here, as we go towards 3, it goes up, and that's how I would do it. Did that answer your questions?
I was just wondering, because we don't know if it's coming from.
You don't know. It does not tell us. And the more calculus we do, there will be questions like this, and there will be more information given, which you will be able to fill in. Like, oh, it actually does a cup thing right here. We know it has to be a cup between here, or oh, it has to be a bump, or whatever, right? And you'll be putting together that kind of stuff. But just given these 5 pieces of information, this is all we could say. And everything else, the only thing really that's going on, we have information here, we have information here, the rest of it is just big question marks. We cannot say. You cannot say what's going on. Cool?
Yeah.
Okay, cool. In fact, it might not even be defined over there. It might only be defined in neighborhoods or very close to those numbers. So, okay. So here's a definition. So we're ready to move on?
Yeah.
Okay, excellent. So here's the definition for today. Definition. Limit as x goes to a of f of x equals infinity means that values of f can be made, I don't know that f of x, can be made arbitrarily large. And by that, by arbitrarily large, we mean as large as you please. Large as you want. 100 million? Yeah, we can make it that big. 700 billion bajillion? Yeah, we can make it that big. As large as you please. By taking x sufficiently close. To a, but not equal to, yeah, or like, but not equal to a. So it's the same kind of thing. We don't really care about what actually happens when you plug in an a. It might be defined, it might not be defined. Just like in the last one, right? We had holes doing this thing. But here at the value in question, which was, I think this one was like 3. There at 3, it gave you this. We don't care about what happens when you plug in there. We just care about what's happening here. Okay? And just like we've already said this must mean that it's going, that in both sides, it's going to positive infinity. Because we don't have a plus or a minus right here. Right? Afterwards. Okay? So, and like I already said, this means, oh, and also, just like we've done before, this can be written like this, as x goes to a, right? And we could say, in this case, the limit of f as x approaches a is infinity. Or, the limit becomes infinite as x approaches a. Or, f increases without bound as x approaches a. So, okay, that right there tells you, when you see that, and this, by the way, works exactly the same with negative infinity. Okay, so we have this up here, and if I put a negative here, I'm going to go ahead and do it. I'll just do it right here. If I put a negative here, this means that the values can be made arbitrarily large negative. An arbitrarily large negative. It's not small, right? Negative 7 billion is not small. You're not making it arbitrarily small. You're making it arbitrarily large negative. An arbitrarily large negative number, right? So an arbitrarily large negative is large and negative as you please by taking x sufficiently close to a but not equal to a, and you would say that f goes to negative infinity as x goes to a. So it's exactly the same thing, right? There's no now, I just wanted to use the positive version here. So if we have this, if a function has this property, then that tells you as soon as you see that, you could say, well, if you're here at a, then your function must do something like this. There must be an asymptote, right? Like we've seen that before. This would be an example of like 1 over x minus a squared. There are other things that do this. Remember the secant and cosecant functions. Tangent does stuff like this, right? Although they split, right? So that's a little bit different. But you could say the absolute value of secant x, that does stuff like this, right? It would be, it would look
tangent
like,
squared or something.
or tangent squared, right? Something like that, you know. And so, okay, that's not really the point I'm trying to make here. The point I'm trying to make is this gives us a nifty definition for an asymptote. So, can I get rid of this definition?
Yeah.
Okay, here we go. Another definition. The line x equals a. That's a line, isn't it? Right? Like, you know, I don't think about that. Like, I think of the line y equals 3. Oh, yeah, that's a line because it's a line. It's y is always equal to 3. But the line x equals 2 is also a line. It's just this line right here. It's a vertical line.
It's not a function.
It's not a function, but it's a line. So we're not talking about functions here in this for this definition. But it is a line. X equals a is a line. It just happens to be a vertical line. Okay. So the line x equals a is called a vertical asymptote. A vertical asymptote of the curve y equals f of x. Now, I just want to go ahead and dispel something here. Whenever I see curve, I think of something that must bend. Like, you know, when I think curve in my mind, I think, oh, something that bends. A curve, if you remember from last year, or I think it was last year, is really any function that you graph, right? So a line is a curve, technically. Like this line right here, y equals 2x minus 1. That is a curve, technically. It doesn't curve, it doesn't bend, but we still call it a curve, okay? So, okay, the line x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following are true. And here are the 6 possibilities. The limit as x goes to a of f of x equals infinity. Or if the limit as x goes to a of f of x equals negative infinity. Or if the limit as x goes to a from the left of f of x equals infinity. Or if the limit as x goes to a from the right of f of x equals sorry, I had it this way. Also from the left goes to negative infinity. Or if the limit as x goes to a from the right of f of x equals what?
Infinite. Positive.
Or if the limit as x goes to what?
A from the left. I'm the
Right. Left.
No.
Plus.
Right.
A from the right.
Plus.
Yes.
Right.
Sorry.
Yeah, because we already got that one. And I messed that up too, 'cause I wasn't, but you get the idea. Is it equals negative infinity, right? So this tells you, this is our definition now of vertical asymptote. Anytime this happens, that's what we're calling an asymptote. Okay? And it does mesh with the definite, if we ever really defined it 2 years ago when we talked about rational functions, I don't know if we ever really did.
Defined asymptote.
Right. I mean, it was like, you know, like when we were doing hyperbolas, you know, we had like this type of thing. And the way that we defined it was like, it will get arbitrarily close to that thing, right? But vertical asymptotes were the ones that are vertical lines, and they had these types of things going on, right? And again, it had the property that the values will get arbitrarily close to that line and go up forever, basically. Okay, so, but this is nice because now we have this nifty definition of a vertical asymptote. Okay, so just now we have all of our definitions, blah, blah, blah. Can I get rid of this?
Yeah.
Okay, so. Number 26. This is from the book. We're going to find the limit as x goes to -3 from the left of x plus 2 x over x plus 3. Now, my intuition immediately is graph this thing, just like we did with the first one. You know, we had 1 over x minus 5.
This one's a bit harder.
I don't know how, I honestly do not know how to graph this. I have some ideas of where I might start, but, ugh, right? Like, you could see how this could easily get really ugly. And so, what I want to do is figure out, so all we care about right now is just behavior as it comes from the left. Okay, and I like to do this. You don't have to do this. I think about a number line, and here's the point, -3. And what we're doing is we're approaching -3 from the left. So my values of x, right, so I'm imagining now we have some value here, and we're calling it x. X lives there on the left-hand side of -3. And so it must be less than -3, right?
Yeah.
Okay, so in other words, x must be less than -3. Now, what we're going to do, we're going to do this analytically, meaning like I'm going to use these symbols with less than or equal to blah, 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 to try to figure some stuff out. And what I want to figure out is, clearly, if I plug in a -3, this thing blows up. So that tells me that there's an asymptote right here, right?
Yes.
Like, you knew this 2 years ago, right? 2 years ago, you could have told me that. There must be an asymptote here when I plug in a -3. So we already know that. So now the only question is, does this thing go up or down? We know it's going to blow up. We know it's going to get arbitrarily large as I plug in values that are really, really close, like -3.000001 plus 3 will give you -0.000001 in the denominator, which makes this thing really, really big. The only question is this going to be a positive number or a negative number? And that's what I'm gonna use this fact right here to try to figure out, and I just think about, okay, all the little pieces of this thing. We have two big pieces. We have a numerator and we have a denominator. And we want to find out, okay, in this range, when x is really close to -3, but on that side of -3, we want to know, for each of these, but we'll just start with the top, we want to know, is x plus 2 a positive number or a negative number? Tell me. Right, because, and what you could just see that and be like, well, -3 is less than 2. And if it's even less than -3, then that's got to be negative, right?
Yeah.
And so you could do it that. I mean, and that's really, I think that's how it would here, right? Since, yeah, it must be the case. Like, x plus 2 has to be less than 0. I mean, you don't need to go into any more than that, right? Really, you don't even need to write that. But we're just going to say, okay, so in other words, x plus 2 is negative. All right, that's part of it. Now let's figure out what happens here. Since x is less than -3, then is that negative or positive?
It's negative.
It's also negative. And one nice way you could see that is like you could get that right here, add that to that side, and you get that that's less than 0, so it's also negative. So when x is in this range, when it's very, very close to -3 and it's on that side of it, we have that x plus 2, x plus 3, we have that the top is a negative number. The bottom is also a negative number, which makes the entire thing what?
Positive.
Positive. It's positive, and it gets bigger, and so no matter, we don't care about what happens at -3, but whenever it's over here, which is the whole thing about a limit, we care about what happens as x gets here. We know it's positive, we know it's getting bigger, and so we could say it must blow up to positive infinity as x gets closer and closer. And that is indeed the answer. This will go positive. And if you're really savvy with this stuff, you could say, okay, and you need to do it this way. You will need to do it this way because you will not have a graphing calculator on a test, and you're gonna see stuff like this. So this is how you should do it. But then, if you're savvy, you go, well, let me just check my work. And so you graph this thing, and you see that, yes, indeed, what happens here at -3, when you graph this thing does indeed look like this. It comes up like this, and it comes down like this. It does. It does. It looks just like this.
It's not loud. Okay.
What's that?
That's not what I thought it was gonna
Yeah, I know. It does though. And that's what I'm saying. Like, I don't know how to graph this. And when I plugged it in last night to Desmos, I was like, oh, who would have thought? I wouldn't have thought that. And so, okay, so that's that one. Everybody get that? Like, this is what we need to do. We need to figure out all the little pieces here. Like what's positive, what's negative, and then how does that play together as this happens. So let's do this one. Now instead of going from the left, we're going to go from the right. And we're going to do the same thing. We're going to say, okay, and you don't need to draw this here, but this is the idea. X is getting closer and closer. And so now our X is on the right-hand side of -3. So what does that mean for X plus 2? So X again, there's -3 and X is on this side of it.
No, we don't really
We don't know.
But we do.
We do.
Because how close are we to -3?
Oh, yes. We're
Arbitrarily
No.
close, right? Like, and that's the hard thing. Because you say, well, if you were only given this, and then you're asked, is this positive or negative? Well, I can't tell you. X could be 1,000,000. But you know that X has got to be less than -2, right? In fact, it's got to be less than -2.99. And as we keep going and keep going, it's going to be less than this, right? And so that's kind of the subtlety of this, is you have to imagine. You're right, if you only knew that X was positive or bigger than -3, you couldn't say anything about this. But we know that we are so close to -3 that doesn't matter. You could pretty much say, well, if it were -3, what would that be, positive or negative? And you'd say, well, this would be negative. Yeah. Okay, so that's the trick there. Now, what about the bottom part? What about X plus 3? Is that positive or negative?
positive.
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 We add 3 to both sides.
Right, because, right, you have this -3, and this one you could actually do, like this is 100% true. You could add this to both sides, and you see, oh yeah, it must be positive, right? So again, that's how you might do it analytically, or you could just think and say, well, it's a bit bigger, not that, I mean, it's it's a smaller negative, right? But at any rate, right, one's negative, one's positive. Therefore, we could say, okay, X plus 2. X plus 3. We know that the top is negative. The bottom, we said, is positive, meaning that the entire thing is
Negative, so it goes down.
and therefore it blows down to -infinity, and so we would say that the limit of this guy is -infinity. Does this limit exist?
No.
No, this limit does not exist. But we could write this to let you know what it looks like there. And now having those two bits of information, you could say, well, since it blows up coming from this side, and it blows down coming from this side, it looks something like this. Now what does it do over here? We don't know. Not sure. But I could tell you that right around here, that's what it looks like. Okay?
So we shouldn't just be plugging in values anymore.
Nope. Not
That
well.
would really work
Not for
this
these.
one.
I mean,
You could plug in values infinitely.
you could right. I mean, that's the idea that like we're shortly will not be plugging in values for anything. We're just going to look at behavior, right? And knowing that just this whole thing about having a limit as x goes to -3 from either side of something over x plus 3, immediately like it's going to blow up or blow down, right? It has to be, right? This is not news to any of us, right? We're familiar with this by now. And so now the only question is, well, what happens? Is it going up or is it going down? And we don't need to actually plug in values to figure that out. In fact, I think it would take longer to type that into a calculator than it would to say, well, it's positive, that's positive. Okay, we're good, it's positive then. Or whatever. Now here's one that you definitely can't graph. Number 28. The limit. Fine. The limit as x goes to 0. Notice is not from the right or left. So right away, they're asking us. They're kind of implying with this question right here that as you go to 0, it's the same regardless if you go from either way. But what we're going to need to do is figure out, is that indeed the case? Because they might be tricking us. This might be a trick. It might be the case that you graph this thing and here at 0, it goes up one way and it goes down the other way. If that's the case, what would we answer?
Does not exist.
You would write D and E, does not exist. But it might be the case that they both go up. Or they both go down. We don't know, so we're going to have to figure out from both sides now. That's what that's telling us, is we need to figure out both sides, because there are 3 possibilities. Because clearly I could see if I plug in a 0, we're gonna have trouble. And so there's an asymptote. But now the question is, well, is it both going up? Is it both going down? Or are they splitting? And so let's do that. When we're really, really close to 0, when x is really, really close to 0, and this is on either side now, this is the nice thing about this, is that positive or negative?
Negative.
It's negative, right? When you're and it doesn't matter what side we're on both sides, it's negative. That's nice. Okay. What about this guy? When we're really close to 0, x plus 2 is positive or negative? When x is really small, is positive. Because I'm imagining that x is like 1 over a billion. Or negative 1 over a billion, right? Add 2, it's going to be positive no matter
Still
what.
positive when you multiply.
And here's the key here. Now, is this thing positive or negative when
Always
x is
positive.
Oh, that's nice, right? We would have some more work to do if it were just x, or if it were x to the 3rd or x to the 5th. Then we'd have to figure this out. But what's nice is we could tell that this thing, so I'm going to write the same way I did before, x squared and x plus 2, that when we're near 0, I'm not going to even say that, near 0, this is negative, and the bottom 2 are positive times a positive, which means that the entire thing is what?
Negative.
Negative. And it didn't matter whether we were coming from the right or the left.
Yeah.
That's nice, so we didn't have to go through and do that. So, what does this mean? This goes to what?
To 0. Well, to negative.
The entire thing, as x goes to 0, the entire thing goes to negative infinity. It blows down. It decreases without bound. And that is the answer. And if you indeed graph this thing, it would look something like this. So there's an asymptote here at negative 2, as you could see, as you expect. There's an asymptote here at 0, and this thing goes this way. It goes like this, and then over here it pops up and then comes back down.
Interesting.
Don't we always have to check both sides? Because here, if it didn't exist, we'd be wrong, right?
Right. If you wrote, and we did check both sides because of the,
yeah.
right? Like, and that's why I was saying, it doesn't matter if it's positive or negative. When you're near 0, this is negative. Positive or negative. And so we did, but we didn't like write it out, right? So that's the big difference right there. But that's what that thing looks like. And indeed, as you go to 0, in both cases, it does decrease without bound. And so this makes sense. Now let's change this a little bit. So let's say almost exactly the same problem, but now this guy's cubed. Same analysis. We have 3 things that are being multiplied together. Right? We have our x minus 1, which near 0 is
Pause. I mean negative.
negative. I almost believed you. Okay. The x plus 2, which near 0 is
Positive.
positive. Okay. Now, so now we're gonna, so actually let's break this up. Now I'm starting to see, ooh, this actually may have a different problem. So let's say when x is positive here, then x cubed is what?
Positive.
Positive. And so in the case where x is positive, so as we're going from the right, then we have minus 1 x cubed x plus 2 is negative, positive, positive. And so this does what? This entire thing is negative, and it does what?
It goes down to negative.
It goes to negative infinity. And so we could say, okay, then the limit as x goes to 0 from the what?
The left. Oh, the right.
From the right of this thing, x cubed, x plus 2, is negative infinity. Now let's do the same analysis, but now take it from the left. So, x minus 1 is negative, as we've said. X plus 2 is positive, because we're very close to 0. Now, when x is less than 0, then x cubed is what? Is negative. And so our x minus 1 over x cubed, x plus 2 is negative,
Over negative times positive.
positive, negative,
Which is positive.
or I did that the wrong way, but you know what I'm saying, which is what?
Positive.
Positive. And so then as we get really, really, really close to 0, this goes towards what?
Blows up.
Regular.
Blows up to positive infinity. And therefore, the limit as x goes to 0 of this thing from the left, x minus 1, x cubed, x plus 2, is negative infinity. And therefore, this limit does not exist.
Wait.
There we go.
Positive. Would it be positive?
Sorry. Yeah. Oh, yes. Yes. Thank you. Thank you. Thank you. Positive infinity. If it were both negative infinity, then it would exist and it would be negative infinity. But in this case, yes. Okay. Everybody get that?
Yeah.
So really good to be able to do this. Hey, is this thing positive or negative? Blah, 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 blah. Okay. Okay, so here's an example. What are we doing? Oh, we're good. Okay, so. Here's an example, and when you go to do your homework, you might think, oh, I know which one this refers to. Not really, but kind of. Yeah, like kind of. I'm addressing it because there's a problem in your homework that's like this, but you'll see it's different. So find the vertical asymptotes. And I'm abbreviating asymptotes like that, because I don't want to write that. I'll misspell it and look like a fool. Find the vertical asymptotes of f of x equals x times secant x.
X times secant x.
I want to graph this thing.
Yeah.
And when you in your
Wait,
book,
we can-
in your book,
can we do
this in your book this would look like this, which is so annoying. They don't right. You're like, what? X x times secant x. Yeah. So that's just the function secant, but then multiplied by x. And
Do you do something like this?
Yeah,
Like you graph it and it's like bounded by. It's like if you multiply two functions by each other, then it's one.
Mm-hmm. And here's the thing about this. We could get really caught up in the weeds of what this thing looks like. Because like I said, my intuition, whenever I'm doing something like this, I want to graph this. That's my first thing. Oh, if I graph that, then I'll know. And to that I'm going to say, the question is, okay, I know what secant looks like. I know what x looks like. So what does taking the graph of secant x, multiplying it by x, what does that do? And the answer in this case is who cares? Really, who cares? Because I'm not trying to graph it. That's not what we want to do. right? If it said to graph this, okay, now we really have to do some work. But all I care about are the vertical asymptotes. Okay, so graphing in this case is not really going to help me accomplish my task. So I'm not trying to graph it. And the thing is, it's asking for vertical asymptotes. So it's only asking for, really, x isn't going to give me any vertical asymptotes, is it?
So if you just graph secant.
Really, if you just graph secant x, then wherever the asymptotes of this guy are, that's going to, unless there's one possibility. There's one possibility here.
If x equals 0.
The only way that you could possibly get rid of an asymptote. So let's just think about just any general function. Forget about secant x for a second. But let's say we have some function that blows up here at, say, 5, like we had earlier. This is a little bit different. But we have some function that blows up or blows down or whatever at 5. If you take that function, call it g, and you multiply it by a function, call it h, okay? You take g of x times h of x, okay, which is what we're doing here, right? We have some g of x. We're multiplying it by something else, some h of x. The only way that you could possibly get rid of this, like, because what's any number, and I don't care what number this is. This might be 100 billion bajillion, okay? But you take that and you multiply it by something that's going to infinity, it's still going to go to infinity, right? It's still going to happen. If you're coming from this side, you take this function right here, just to the left of it, I don't care what value it is, if these values are getting bigger and bigger negative, well then when you multiply it by some finite number, it's still going to be going to the bigger negative number. The only possibility you have of getting out of this trap is if at this point your h is going through 0. And then the question is,
What's 0 times infinity?
yeah, what is 0 times infinity? And we will address that later on in this class. So and we will, like you'll see, we'll talk about limits of that type of thing where whatever. But that's later. That comes later. The point is, we can't really say what does happen. And so let me give you an example. I'd like to make this a little bit more concrete before we get to the actual problem that we're working on. What do I mean? And my claim is that given any two functions that do that, one's going to, say, infinity, or negative infinity, but we're going to use infinity, and one's going to 0, what happens to the asymptote? And so, for instance, here's an example. 1 over x squared has an asymptote at x equals what?
0.
Uh-huh. And so it looks like this, right? And now, let's think of a function that equals 0 at 0.
Sine of x.
Or how about just x?
Oh.
So x is equal to 0 at x equals 0, okay?
Wait, so x over x.
And so let's see what happens. Let's just see what happens. Let's just take that function and multiply it by the function with the
That's just
asymptote.
1 over x.
Does it still have an asymptote?
Yeah.
Ooh, it still has it. So the new thing that we got actually still has an asymptote. Ooh, interesting. But now, okay, so you might think, aha, it's gonna still have an asymptote. But check this out. 1 over x has an asymptote at x equals 0. And the function x equals 0 at x equals 0. And so what happens when we multiply those guys together?
Did you just get 1?
You get 1. Does that have an asymptote?
No.
No, it's just the function 1. So on one hand, multiplying an asymptote by a function, multiplying two functions together. One has an asymptote at 0, one is 0 at 0. In one hand, you still got an asymptote. On the other hand, you took a function that has an asymptote at 0, and another function that's 0 at 0, and you got rid of your asymptote. My point is, you do not know yet. We will be able to deal with it. later on in this class. We will have the tools to be able to address that, but we don't now. Luckily though, who cares? Because that's not going to be a problem here. Let's look at secant. So secant is 1 over what?
1 over
Cosine.
Cosine. And cosine looks like this. Yeah. And so 1 over that is the thing that, and so I'm thinking, okay, whenever it's 0, you're going to get an asymptote. Where is it 0? Which number is
Pi
this?
over 2.
Pi over 2. There's another one right here, which is at where?
3 pi over 2.
3 pi over 2.
So it's going to be infinite.
And what about here?
Yeah. Negative pi.
Negative pi over 2.
Negative 3 pi.
And negative 3 pi over 2. Okay. And so secant looks like this. And so on forever. That picture repeating forever and ever and ever. Now, I could ask myself, what happens when I multiply the function x there? Well, who cares? There's no asymptote. It asks me about asymptotes. I multiply this function by a function that's 0 here. Well, there's no problem. It'll just go down to 0. But that's not what it's asking about, so I don't need to worry about it. The only thing we had to figure out is that x isn't going to kill any of these asymptotes, right? Because if I plug in, we'll just have a pi over 2 times secant pi over 2. Still bad news right there, right? That hasn't changed the fact that secant of pi over 2 does this thing, blows up, does not exist, whatever, right? So that's my long-winded way of saying this one's pretty easy because this thing does not modify the asymptotes, okay? And so we could say the asymptotes are when x...
Pi over 2 plus pi times n.
Pi over 2 plus what?
Pi times n.
Maybe, I don't know, 2 pi n. I'd rather do it this way. I mean, maybe you're right. You're probably right. In fact, I'm certain you're right. I just don't want to think about it too hard. You know what I mean? I'm going to look at one full period and say, where are the problems? There. Okay, so then there, minus 2 pi, minus 4 pi, there, plus 2 pi, and so on and so forth. I think you're right. I think it's off because it's off by pi, and so you just do that. You're right. I'm not doing it. I don't trust myself. I'm going to lose something. So, that's it, right? It just happened to be the case that there was no asymptote at the only place that x could have killed an asymptote.
If it were like cosecant.
But if it were cosecant, did I write that down? Oh yeah, I did. Yeah. And I did. And so here we go. However, x cosecant x. What about its asymptotes? Because now cosecant does have an asymptote there and at 0, right? So cosecant x, it does this thing here. So there's pi, comes back around like this, right? And there's negative pi. Oops, negative pi. Yes, negative pi. And so now the question is, okay, well now I'm multiplying by x, and x is 0 at 0. So what happened? What does that do? Ooh. And so in other words, what we're trying to figure out is what is the limit as x goes to 0? It looks like it's going to be different from either side, so maybe I want to ask what happens here as x cosecant x. What does that do? We will be able to answer that in a couple months maybe, but that will be something that we will study. What does that do? I don't know. What's 0 times infinity? What's 0 times positive infinity? What's 0 times negative infinity? Well, it depends. It depends on how fast this guy's going to 0 versus how fast this guy's going to infinity. So, and I think I said this in algebra too. It could be a lot of different answers. It could be infinity. It could be negative infinity. It could be 0. It could be any number. Really, we don't know. We have to do our work and figure that out. And we'll figure out how to do that. But anyway, so that's it. These are, oh, by the way, I didn't tell you. These are called infinite limits. So limits that spit out an infinity, we call them infinite limits. And that's that. That's all I got, you guys. So, any questions?
No, I don't think so.
No? Awesome. All right. You guys have a good one.